Hello, welcome to the lecture for section 5.3. And we're skipping a couple sections in chapter 5. So before we talk about the material in 5.3, I want to spend just a couple of minutes reviewing some background information that's necessary for this section. All right, so let's start with a few definitions. The measure of an angle. We have an angle drawn right here. The measure of that angle, it's the measurement between the two intersecting lines or line segments, or maybe we can think of them as rays. All right, we start at the initial side, which is the horizontal, okay? It ends at the terminal side, that's the other side, all right? It's a rotational measure, not a linear measure. All right, we measure angles in two different ways. We can measure them with degrees. We have an angle that's measured 25 degrees. We might also measure angles with radians. Say something like pi over 2 radians. More on radians later. All right, the arc length. An arc length is actually a distance measure. An arc is the area along a circle, right, that is across from an angle that's bounded by 2 radii of the circle, right? All right, so it's a portion of the circumference of a circle in between the two sides of an angle. Okay, one of the measures of an angle is with radians, right? And a radian is actually a ratio. It's just a ratio. It's a ratio of the length of an arc over the radius of a circle. All right. Now, because it's a ratio, we don't have to use units when we refer to radians. Sometimes we do, but a lot of times a radian will just be displayed as a value, and it will often have pi in it. All right, so consider a circle with a radius 1. We call this the unit circle. All right, then the circumference of this circle, by the formula for the circumference, is 2 pi r, or 2 pi times 1. Thus, the measure of the angle that is one whole circle, right? So if we start here and we go all the way around and end where we begin, that measure of that angle of the entire circle is going to be 360 degrees or 2 pi radians. Okay, halfway around the circle is going to be half of 360 or 180 degrees, or just pi radians. All right, and if we only go a quarter way around the circle, that's of course a right angle, right? That's going to be 90 degrees or pi over 2 radians. All right, we can convert radians to degrees and degrees to radians. To convert radians to degrees, we simply multiply by 180 and divide by pi. All right. To convert degrees to radians, we want to multiply by pi and then divide by 180. All right, so a couple of examples. If we want to convert pi over 3 radians to degrees, we want to multiply that pi over 3 by 180 over pi, 180 degrees over pi, right? Of course, the pi's will divide out, and 180 divided by 3 is just 60 degrees. All right, if we want to convert 7 pi over 4 radians to degrees, no difference there. Just do the same thing. 7 pi over 4 times 180 over pi. Right? Pi's will divide out. Let's see, what is, let me see, 7 times 180 divided by 4. And let me put that in my calculator here real quick and find out what that is. 315 degrees. All right. Now, if I want to convert degrees to radians, I'm just going to multiply by pi over 180, right? So converting 120 degrees to radians, I'll just multiply 120 by pi over 180. All right, so what do we have there? It's 120 pi over 180, and that's going to reduce. That's going to reduce down to 2 pi over 3. All right. 225 degrees to radians. Yeah, there's nothing different about that. You can do that one on your own. All right, and one more concept that I want to review with you, and that's the concept of the quadrants of the Cartesian plane. This can be very important as we study trigonometry. We have the 4 quadrants of the Cartesian plane, starting with the upper right. We have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. What's important here is that in quadrant 1, both x and y coordinates of any points will be positive, right? Positive x and positive y. Over in quadrant 2, though, the x coordinates are going to be negative and the y coordinates are all going to be positive, right? X are negative because we're left of the vertical axis. Down in quadrant 3, all the x's and all the y's are negative. And over in quadrant 4, the x's are positive again, but the y's are negative. All right, quick review. Now let's go ahead and start with the concepts in with the contents, of section 5.3. Okay, points on circles using the sine and cosine. All right, so if we consider a circle here, I've just got a portion of a circle shown, right? And there's a point on that circle. That point in the Cartesian plane would have an x-coordinate and a y-coordinate with some value, right? We'd have our vertical, our y-axis, and our x-axis. All right. Now that point, if I drew a radius, right, from that point to the center of the circle, and then dropped a perpendicular from that point to the horizontal, right, it's going to make an angle here, theta. All right. And we can define, there's 2 functions that we can define that use that angle as their input. There's the sine of theta, and the sine is defined as the y-coordinate of that point over the radius. The cosine is defined as the x-coordinate of that point over the radius. All right, so let's look at an example of finding the sine and the cosine for some point that's on a circle. All right, well, let's see. If we have this circle and it's sitting on the Cartesian plane, right, with the origin being the center of that circle, and we have a point that has an x-coordinate of 3 and a y-coordinate of 4, and it sits on the circle, all right, so it's on the circumference of that circle. Let's say that point is, I don't know, maybe right there. We'll put it right there as the coordinates. X is 3, y is 4, all right? Now the radius of that circle is 5, okay? And the angle, we're going to call that angle that it makes with the horizontal theta. All right, to find the cosine of theta and the sine of theta, right, we're just going to use the ratio as we're just going to use their definitions, the ratio of their definitions. So let's see, our radius was 5, right? The sine of this angle theta then is going to be the y over the radius, right? So that's going to be 4 over 5, 4/5. The cosine of theta, that's going to be the x-coordinate of that point, or 3 over 5, 3/5. So I don't know what that angle measure is. We'll talk about how to find those angles later. But I do know that the sine of that angle theta is 4/5, and the cosine of that angle is 3/5. Okay, let's look at another example. Here we have some point P that's on the unit circle. All right, the unit circle has a radius of 1. Right, we know the y-coordinate of that point is negative 3/5, and we know that point's in quadrant 4. What would that x-coordinate be? Well, let's see. Let's draw it. Here's our circle. Okay, our radius is 1. We have this point where the y-coordinate, or the y, is negative 3/5. All right, well, where would that be? Where would a y be negative 3/5? It's got to be down here below the x-axis, right? And we're being told that that point is in quadrant 4. All right, so I'm going to put it somewhere maybe right there. I don't know what that x-coordinate is, but the y-coordinate is negative 3/5. All right, my radius is just 1. And if I drop a perpendicular with the horizontal axis, I can make a triangle there, right? The legs of these triangle, this upper leg is going to have a measure of x, whatever that value is at that x coordinate. Okay, the vertical leg there will have a measure of y, right? Because that's our y distance, right? And we know that y is 3/5. Right? So how can I find the value of x? Well, you all remember the Pythagorean theorem? Oops. The Pythagorean theorem, some of us learned it this way, a squared plus b squared equals c squared. But what that's really saying is for a right triangle, one leg squared plus the other leg squared equals the hypotenuse squared. So look, I've kind of made a triangle here. If I just sort of blow that up, that's supposed to be a right angle. Let me try that again. I didn't do it very well. If I make that triangle like this, I'm just going to blow up that little triangle that I drew inside the circle, right? There's my right angle. The hypotenuse then is going to be over here. That's going to be the radius of that circle. So it's just going to be 1. All right. This top leg, we don't know what that one is. It's x, but we do know that the leg across from the hypotenuse over here, the vertical leg, measures 3/5, right? I'm not worrying about the negative right now because it's really just the measure of a triangle, a leg of a triangle. I can now use the Pythagorean theorem to find the value for x, right? I can say that, what was that? Get that big again. There we go. I can say that x squared plus 3/5 squared equals the hypotenuse squared, or 1 squared, right? So x squared plus 9/25 would equal 1. Let's subtract the 9/25 from both sides. So x squared is going to be 1. Let's write 1 in 25ths. So we'll say it's 25 over 25 minus 9 over 25. All right. Then that x squared is going to be 16/25. That means that x, if I take the square root of both sides, is going to be either positive or negative. See, square root of 16 is 4. Oh, that was supposed to be a 5, and I wrote a 4. Let's fix that. 4/5. All right, positive or negative, which one is it? Is it positive or is it negative? It's the x coordinate, and we're over here we're right of that vertical axis, so it's the positive 4/5 that I want. Okay. All right, and here's a list of several common sine and cosine values for 0 degrees, right, which is also 0 radians. The sine will be 0 and the cosine will be 1. Right? For 30 degrees, we've got pi over 6, 1/2, square root 3 over 2. Right? Here's 45 degrees. The sine and the cosine are the same at 45 degrees, or pi over 4. Does that make sense? Yeah, because if we make a triangle there, it's going to be an isosceles triangle, right? So these two angles would have to be the same. Okay. 60 degrees, we have pi over 3, square root 3 over 2 and 1/2, and then there's 90 degrees. All right. So let's take a look at finding the coordinates of a point on a circle. All right. If for any given angle, right? If we consider the definition of the sine and the cosine, remember the definition of the cosine of some angle, it was x over the radius. Well, if I multiply both sides by the radius, I can then say that x, the coordinate of the terminal point of an angle on a circle, right, x is going to be equal to r times the cosine of theta. Right? I could do the same thing with the sine. We said the sine of theta was y over r, and if I multiply both sides by r, I have this definition for y. It's going to be r times the sine of theta. All right. So in a unit circle where the radius is 1, the x coordinate of the point is the cosine of theta. and the y-coordinate of the point is the sine of theta. All right, now we're not going to prove a whole lot of identities in this class, but this one is pretty cool. And this is the first, maybe even the most important identity that we use in trigonometry, and that's the Pythagorean identity. Okay, all the trig identities have fairly, well, some of them are, no, they're not really that difficult. The proofs are really not difficult. And I think your textbook has quite a few of them. You can Google others that you won't find in your text. But I do want to do just this one with you, just because I think it's really cool how all this connects. Right? So this is the Pythagorean identity is listed here. Sine squared of theta plus cosine squared of theta equals 1. All right? But why would that be the case? Well, think about your Pythagorean theorem, right? The Pythagorean theorem that's saying a leg squared plus leg squared plus a hypotenuse squared. Well, in the unit circle, that hypotenuse squared is going to be 1, right? But we could say x squared plus y squared equals for any, it'd be the radius for any, it doesn't have to be the unit circle. If we're thinking any circle, it's just going to be r squared, right? And that's just your Pythagorean theorem. We've been dealing with that for a long time, probably. So given that, and since x is now defined as r times the cosine of theta, we can substitute x in here, or I'm sorry, we can substitute r times the cosine of theta in here for the x, and we can say r cosine theta squared, and for y, we'll substitute r sine theta in, right, plus r sine theta squared is equal to that r squared, right? Now let's just simplify. These two terms are being squared. Let's just distribute that squared. Let's call this r squared times the cosine of theta squared. And when we write, when we square a trig function, we usually say, we put the square here, we say cosine squared of theta instead of putting the square after, because it's hard to differentiate between the cosine of theta squared and the cosine of theta, the whole thing being squared. So we just say cosine squared theta when we want the whole thing to be squared. All right, so this will be r cosine squared theta, r squared cosine squared theta plus r squared sine squared theta equals r squared. Now all we have to do is divide everything by r squared, and we have a Pythagorean identity. So cool, right? Let's see, what is it? It's the cosine. All these r squareds, they divide out. Of course, r squared divided by r squared is 1, right? So the cosine squared of theta plus the sine squared of theta is equal to 1. All right, we will use this identity quite a bit in this course. It's very useful when you know the value of the cosine and you want to find the value of the sine, or if you know the value of the sine and you want to find the cosine. All right. Okay, so let's look at finding the coordinates of a point on a circle. Let's see if we can use, not necessarily Pythagorean identity, but let's take a look at these two new equations that we just found, or these two new definitions for that x and y coordinate, right? We say that x is equal to r times the cosine of theta, y is equal to r times the sine of theta. All right, so if we have a circle with a radius of 5, all right, and we can use these definitions to find the coordinates of the point on that circle on the terminal side of the angle that's pi over 3. All right, well, let's draw it. Here's our circle sitting on the Cartesian plane, right on the origin. All right, pi over 3 is maybe about right there. Okay, there's our angle. We want to find the coordinates of this point, right? The coordinates of this point, the x and the y coordinates. Okay, well, we know that the radius of this circle is 5, right? The radius is 5, so I can simply use these formulas. My x coordinate is going to be 5 times the cosine of pi over 3, which is the cosine of pi over 3. Now I can put that in my calculator, but I want to be careful doing that because I won't have an exact answer. I won't have an exact answer. Let's go back and look at some of these common values that were calculated in this table for us, you know, based on, where is it? Based on the definition, right, of the sine and the cosine. All right. Well, pi over 3 is right here, 60 degrees. We can see that the sine, that ratio, is square root of 3 over 2, and the cosine is 1/2. Right. So cosine is 1/2, so x is then going to be 5 times 1/2, or 5/2. Okay. That y coordinate is going to be 5 times the sine of pi over 3, which, if we were to calculate that using the ratios, would be, or using the definition, it would be the square root of 3 over 2. It's that ratio there. Oops, times 5. So 5 square roots of 3 over 2. All right. Now, we can use this idea of the signs of x and y coordinates changing in the quadrants to find the trig functions for angles that are in quadrants other than 1, in quadrants 2, 3, and 4, right? So on the unit circle, recall that the x coordinate is the cosine of the angle, it's cosine of theta, and the y coordinate is the sine of theta. Okay? So given that, for in quadrant 1, all cosines are going to be positive, and all sines are also going to be positive, right? If we look down here in quadrant 4, right? In quadrant 4, all x and all y coordinates down here, the x's are going to be positive, but the y's are all going to be negative. So we can say that all cosines are positive in quadrant 4, but all sines are negative. Over here in quadrant 3, all sines and cosines are negative, because all x's and all y's are negative. And then up here in quadrant 2, the x's are negative, but the y's are positive. So we have negative cosines, and we have positive sines. All right, so given that, can we use an angle in quadrant 1 to determine a sine or cosine in any of the other 3 quadrants? Right? Well, look at this first diagram here. You have angle theta, okay? It's a quadrant 1 angle. It terminates here. It has an x and a y coordinate. The cosine will be whatever that x is. The sine will be whatever that y is, right? But look at this angle alpha here, this larger angle that goes over here into quadrant 2, right? Look at that terminal point. Wouldn't those y coordinates be the same? Yeah. And what about the x? Look, it's the same distance from the vertical axis, but over here in quadrant 2 and 3, the x's are negative, right? So here in quadrant 1, if we have a positive cosine of theta and sine of theta, the values for that larger angle that has the same absolute value x and y coordinates, you're going to have a negative cosine theta and a positive sine theta. Okay. I can do this in the other quadrants as well. Look in here, look at the over here in this example. We've got angle theta, same angle. But look, if we go all the way around here to angle beta, this large angle here, and we consider those x and y coordinates there, look, the x is going to be the same, isn't it? Because it's the same horizontal distance for that terminal point. The y, however, will be the negative of whatever it was up there. All right? So that means angle beta, or I could say it this way. I could say cosine of beta is equal to the cosine of theta, right? And I could say the sine of beta is equal to the negative, or negative of the sine of theta. So these angles that have the same absolute value of cosine and sine share the same reference angle. All right, what is a reference angle? A reference angle is the smallest angle to the horizontal axis that is made by the terminal side of an angle, right? So over here in quadrant 1, the reference angle is always going to be the same as angle theta, or as the angle itself. But if, ooh, I have a problem with my tablet today, folks. Let's try that again. But if I consider, let's see, what was I doing? Oh, if I consider this larger angle, let me draw this one in now. We'll call this guy beta. This angle beta, it has the same sine and the negative cosine as we looked at on the previous page. And we determine what those are based on the reference angle. Look, for angle beta, its reference angle is theta. It's going to be the same as that one over there in the first quadrant. Okay? So for angle beta, this is the terminal side here. That's the terminal side. The reference angle for beta is this theta here because it's the smallest angle between the terminal side of our angle and the horizontal. All right? If I have an angle that terminates, here, let me draw it way outside. If an angle that terminates way over here, I don't know, maybe that's like 240 degrees or something like that, way over here, right? The reference angle for this guy is the smallest angle between this terminal side and the horizontal axis, and it's going to be the same. It's going to be theta again. I can have an angle way over here in quadrant 4. Maybe it's this one going all the way around there. I don't know, maybe it's 300 or 315 degrees, something like that, right? Call that guy alpha, right? That big angle alpha, its terminal side is here. The reference angle, again, is theta because that's the smallest angle between the terminal side and the horizontal. All right? So let's look at an example using reference angles. All right? If we have an angle of 240 degrees, we can use a reference angle to find the sine and the cosine of 240 degrees. All right? So let's see, where does 240 degrees fall? All right, well, all the way around is 360. Halfway around is 180. 3/4 of the way around over here is 270. So 240 somewhere right in here. We'll say this is 240 degrees. Okay, so here's the angle, 240 degrees. It always starts here in quadrant 1 on the horizontal. Goes all the way around. The terminal side is here. What is the reference angle for 240 degrees? The smallest angle between 240 and the horizontal is this guy here. How can we determine what it is? Well, easy. It's just 240 degrees minus 180 degrees, right? What's that? 60 degrees. Okay. So, what would if I knew the sine and the cosine for 60 degrees, what we'll do, it's up here, there it is. Sine is square root 3 over 2, cosine is 1/2. All right, so here, let's just write those. The sine of 60 degrees is square root 3 over 2. The cosine of 60 degrees is 1/2. All right, given that, what is the sine of 240 degrees going to be then? Right? Well, 60 degrees, let's think about this for a minute, is right here. That's this part of it, right? We call that 60 degrees. Okay. It's x and y coordinates, or it's sine and cosine. Let's see, cosine correlates to the x coordinate. We're going to say this is a unit circle. All right. So the cosine would be 1/2, and the sine would be square root 3 over 2. Okay, they're both positive in quadrant 1. Well, what's happening over here in quadrant 2? They have the same reference angle, right? This angle here equals this angle here. So we know we have the same absolute value of the sine and the cosine, or the x and the y coordinate. If it's just a unit circle, we're saying this one is. All right? But over here in quadrant 3, x's over here are negative, right? And y's are negative. So these have to be negative. So then the sine of 240 degrees has to be negative square root 3 over 2. It's going to be the negative of the sine of its reference angle. And again, that's because we're down here in quadrant 3. All right? The cosine of 240 degrees, cosine of 240 degrees is going to be negative 1/2. Right? And again, when we're dealing with the unit circle, right? If the radius is 1, then if x equals the cosine times the radius, right? The x coordinate of any terminal point is going to be the cosine of that angle where that point terminates, right? And the sine is going to be the y coordinate of that terminal point, just for the unit circle. All right. So speaking of the unit circle, here's a summary of common sines and cosines on a unit circle, right? I would highly recommend that you print this out. You have it on a formula sheet in Blackboard under class information, right? Or you can just Google it and print one out. Very, very easily, you can quickly look at this to find a sine or cosine of many common angles that are used, right? Again, the cosine is the x coordinate, the sine is the y coordinate of wherever that angle terminates. All right, so let's look at an example. If you see in My Open Math, if you see a question that asks you for an exact answer, do not pull out your calculator, right? Because it's probably gonna involve a radical that is an irrational number. That decimal is going to go on forever and ever. And you will not be able to specify that in an exact form if it's a decimal, right? So if you see the word exact anywhere, make sure you're using this unit circle to find your value, right? Or the formula if you're calculating. All right, so let's see, what does it say? Find the coordinates of a point on a circle with a radius 1. Okay, good, here's a unit circle, corresponding to an angle of 5 pi over 4. All right, well, that's fine. We always start here. And then we go around this way until we find the angle. We go counterclockwise till we find the angle we want. All right, so 5 pi over 4, let's see. There's pi over 2. There's pi. There's 3 pi over 4 pi. Here's 5 pi over 4 right there. Okay, so this is the angle. It's going to terminate right there. All right, that's the angle, 5 pi over 4. It's equivalently 225 degrees. All right, what are the coordinates of the point? Negative square root of 2 over 2 and negative square root 2 over 2. Right? Let's write it. Okay, find the coordinates of a point on the circle with the radius of 6. Ooh, okay, it's not the unit circle anymore, corresponding to an angle of 5 pi over 4. Well, what does that mean? Well, remember the definition for x is simply r times the cosine. And remember that y is simply r times the sine. Well, on the unit circle, the sine and the cosine are those coordinates of that terminal point. So if the radius is 6, we're just going to multiply them by 6. It's going to be negative 6 square roots of 2 over 2. And then, again, that's kind of weird. I should probably reduce that. And I should write this as negative 3 square roots of 2, negative 3 square roots of 2. Okay. Now, we will use the calculator sometimes. If you are dealing with an angle that's not on this unit circle, you'll have to use your calculator to find a sine or a cosine. Be very careful when you do that, though. Please make sure that you're in the proper mode. You will have you have a mode key on your calculator. Whichever model you're using, you do have a mode key. Press it and look, you'll see, I don't know, a couple lines down, somewhere along the way, it'll say radian or it'll say degree. I think it's rad or DEG, something like that you'll see. If you're dealing with radians, like we were here, 5 pi over 4, it did not have a degree symbol, so it had to be radians. Okay, you would want to be in radian mode. If you're dealing with degrees, let's see, like we were here, we didn't use the calculator on these, but if we did, we would want to make sure that we're in degree mode. Okay, all right, that ends the lecture for section 3.4.